Hey you twats! Yes, you! Are you cooked for your midterms? Then you found the right video. Today, I'll be teaching you basic linear algebra because boo-hoo university lectures are too confusing for a single-celled organism brain. Here's the game plan. First, we'll look at what a linear equation even is. Then we'll carve our linear systems, pretend to care about their solutions, and wrap it up with augmented matrices and elementary row operations. Yeah, I know, sounds like a lot, but I'm sure you can handle it, baby. Alright, first up, linear equations. What is a linear equation? In case your goldfish brain can't remember, a linear equation is an equation, though, that contains variables with exponents of 1. The value wrapped in front of a variable is known as a coefficient, and a standalone value like 3 is called a constant. To attain standard form, shove all variables together with their coefficients to one side of the equation, and constants to the other side. Easy, right? No? Then maybe it's time to click off this video and go memorize your multiplication table. This linear algebra stuff might be a bit too much of a big boy concept for you. Now, introducing linear systems! Because one equation wasn't painful enough, we decided to stack a few together for maximum suffering. What is a linear system? A linear system is a system that contains multiple linear equations. Wow, shocker! For example, here we have 3 linear equations that fall under the same linear system. Do you care? Probably not, but you have to pass your exams, so keep pretending. Here's the generalized version of a linear system. In general, a linear system with n variables and m equations has the following form. We have variables x1 to xn with their corresponding coefficients in each equation. Since we have m equations, we will make m copies of the linear equations equating b1 to bm. Got it? Don't think so, but we're moving on anyways. If there are no constant terms, a linear system is homogeneous. It means the equations are all just floating around in math limbo, much like your GPA after midterms. Next up, we move on to solutions to a linear system. There are 3 types of solutions to a linear system. The first type of solution is a unique solution. This means that there is only one set of solutions to the linear system. For example, in the given linear system, when we solve for x, y, and z, we will get x equals 1, y equals 2, and z equals 3. There are no other possible sets of solutions. The second type of solution is a general solution. It means that there can be more than one possible solution to the linear system. You'll usually see this when you have more variables than equations. Just like when your professor assigns 10 assignments but only gives you 5 lectures to explain them. In the given linear system, we have 3 variables, x, y, and z, and 2 linear equations. In order to solve the variables, we introduce a parameter to a variable. Let's call it s, because why not? In this case, we let z equals s. After which, we solve for x and y as though we are dealing with 2 simultaneous linear equations containing variables x and y only. As a result, we will obtain x equals half plus 1/6 s, y equals negative half plus 5/6 s, z equals 2s, where s is a real number. And boom! We get infinitely many solutions. Kinda like the infinitely many ways you can procrastinate instead of studying for your exams. For a general linear system with n variables and m equations, we can say that C1, C2, Cn are possible solutions of x1, x2, xn in the linear system. Upon substituting the variables with their corresponding solutions, we can transform the linear system as such. As long as the linear system has a solution, we can say that the linear system is consistent. The third type of solution is simply no solution. Just like the way for you to find a Valentine's this year, this linear system has no solution, as 1 equals x plus y equals 0 is not possible. If the linear system has no solution, we can say that the linear system is inconsistent. Just like your sleep schedule. Now, moving on to the next concept, augmented matrix. Because is math still math if it doesn't make things look even more complicated? Well, fret not. An augmented matrix simply represents linear equations in matrix form. Imagine some ancient fossil got tired of writing out math equations and decided to compress them into a cold, soulless grid. That's an augmented matrix. For example, in the given linear system, we will focus on the coefficients and the constants in the linear system. An augmented matrix will contain a vertical line. Entries before the vertical line will be the coefficients. Entries after the vertical line will be the constants. In the first row of the augmented matrix, we will have coefficients such as 2, -4, and 3, and the constant 3. In the second row of the augmented matrix, we will have the coefficients 1, 1, and -1, and the constant 0. In the third row of the augmented matrix, we will have the coefficients 3, 1, and 2, and the constant 11. In general, for a linear system with n variables and m equations, the augmented matrix can be expressed with its first row containing coefficients a11, a12 until a1n, and constant b1. The second row contains a21, a22 until a2n, and constant b2. And so on and so forth until the last row, which contains am1, am2 until amn, and constant bn. Finally, we are nearing the end of the lesson. Phew, teaching you bozos was harder than I thought. For the last section, we will have elementary row operations. The first operation that we can perform on an augmented matrix is to exchange two rows. In the given augmented matrix, we want to exchange the second row with the third row. Hence, we will copy the entries in the second row of the given matrix to the third row of the new matrix and copy the entries in the third row of the given matrix to the second row of the new matrix. It's like magic! Except it's just basic math. The second operation that we can perform is multiplying a row by a non-zero constant. In the given augmented matrix, we want to multiply the third row by 3. The first and second rows of the matrix do not change. When it comes to the third row, however, each element will be multiplied by 3. This results in the coefficients becoming 9, 3, and 6, and the constant becoming 33. Basically, you can make an entire row bigger or smaller. Kinda like inflating your confidence before an exam, and then watching it deflate as you start reading question 1. Now, what happens if we multiply a row by 0? In the given augmented matrix, let's say we want to multiply the third row by 0. The first and second rows of the matrix do not change. When it comes to the third row, however, it will become a 0 row. Good job! Now you've ruined it. You've changed the whole linear system from having a unique solution to a general one. Way to go, genius! The third operation that we can perform is adding a multiple of a row to another. In the given augmented matrix, we want to add 3 times of the third row to the second row. In the notation, it is important to note that we will perform the operation on the first row mentioned, which, in this case, refers to the second row. In the new matrix, we will simply copy the same entries for the first and third row. For the second row, the entries will be 1 plus 3 times 3 equals 10. 1 plus 1 times 3 equals 4. Negative 1 plus 2 times 3 equals 5. Followed by 11 times 3 equals 33. Alright, some of y'all math nerds might ask whether elementary row operations are commutative. Well, it depends. In some cases, no. When we need to exchange rows, the sequence of the operation matters. In the given augmented matrix, we want to first multiply the third row with 3, and then exchange the second row and the third row. This will give us 9, 3, 6, and 33 for the second row, and 1, 1, negative 1, and 0 for the third row. However, if we first exchange the second row and third row and then multiply the third row with 3, we will get a different result. We will get 3, 1, 2, and 11 for the second row, and 3, 3, negative 3, and 0 for the third row. The second case where elementary row operations are not commutative is when we need to add a multiple of a row to another. In the given augmented matrix, we want to add 3 times of the third row to the second row. We will get the following matrix. However, when we switch the operation, it becomes multiplying the third row by 3, and then adding the second row to the third row. As such, we will get the following matrix instead. Blah blah blah. Yeah, we get it. So, will elementary row operations ever be commutative then? To answer your question, they are only commutative if we are only multiplying a row with a non-zero constant. Whether we multiply the third row by 3 or the second row by 2 first, the order doesn't matter. They will give the same result. Amazing! A rare win for math! Should the elementary row operations be commutative, we can shorten what we need to write by stacking the operations as such. Wow, efficiency in the math equation? Incredible. Who made that was lost? Alright nerds, that's a wrap on today's lesson. Congratulations! You survived another lecture without your brain fully imploding. Probably, if you actually learned something new today, miraculous job! Maybe there's hope for you after all. If not, well, that's a skill issue right there. Review your notes, rewatch the video, or just accept your fate. Anyways, if you enjoyed my teaching, suffering, share this video and give it a like. Or don't. I'm not your mom. But if you don't subscribe, I'll personally haunt your text perfect head. Well, you can avoid. Aight. See you losers!